6.6 is on L'Hopital's rule, and L'Hopital's rule is a tool that helps us evaluate limits that when we use direct substitution, we end up with indeterminate form. Meaning, if we use direct substitution, we end up with 0 over 0 or infinity over infinity and so forth. So I'm going to start with the proof that covers 0 over 0. I'm not going to do the infinity proof. I think one is enough to convince you that this strategy makes sense and is logical. So this proof, which is mostly pasted below for you, I'm just going to add on to it a little bit and explain as we go, covers the indeterminate form of 0 over 0. So given that f and g are continuous and differentiable functions at c, which is a real number, such that f of c is equal to g of c, which is equal to 0, aka we get indeterminate form when we plug in c, and that the limit as x approaches c of each of those is 0 as well. That's what creates this indeterminate form as well. So first of all, we can say that the limit as x approaches c of f of x over g of x is equal to the limit as x approaches c of f of x minus 0 over g of x minus 0. And this is one of those proofs where sometimes you should be wondering, well, why would I write it this way? How does this help me? So the reason that this helps me is that by doing this, we can substitute in the fact that f of c is equal to 0 and g of c is equal to 0 into the next step. So I'm going to put that down there so you can see what I mean. So again, we want to say f of x minus 0 over g of x minus 0 so that we can use this fact up here. Whoops. We can use this fact up here and substitute in f of c and g of c into the next portion. So it follows that the limit as x approaches c of f of x over g of x is equal to the limit as x approaches c of f of x minus f of c, which is just 0, over g of x minus g of c, which is just 0. And then I'm not really sure why my Word document moved my x, kind of messed up my x approaches c, but that's okay. So what I'm going to do now is I'm going to multiply both the numerator and the denominator by 1 over x minus c. Over 1 over x minus c. So the reason that I'm multiplying both the numerator and the denominator by 1 over x minus c is because then what I'm really getting is, I'm going to write this off to the side, I'm really getting the limit as x approaches c of f of x minus f of c over x minus c. That's going to be my new numerator, and that whole thing is really over the limit as x approaches c of g of x minus g of c over x minus c, and all of that should look really familiar because that is basically, well, no, not basically. That is the definition of derivative, which is how we get here. So by multiplying the top and the bottom of the fraction by x minus c, we end up with the fact, and this is the big fact, this is L'Hopital's rule, that the limit as x approaches c of f of x over g of x is equal to the limit of the derivative of both functions by the alternate definition of derivative. So we substituted in f of c and g of c, since those are equal to 0. We then multiplied the numerator and the denominator by 1 over x minus c, which we're allowed to do because that's 1 over x minus c over 1 minus 1 over x minus c. Again, is still just 1. We're allowed to do that to be able to say that these derivatives are true. Now, what I want you to remember was this started with the fact that both of these limits in f and g originally were 0. That's a huge component in here. You can't just go taking derivatives because you feel like taking derivatives. The limit of the numerator function and the limit of the denominator function both have to be 0. And this is called L'Hopital's rule. A couple of hints, reminders, things that you should know about using L'Hopital's rule. You always have to start by using direct substitution. You have to have indeterminate form. And you cannot write that something is equal to 0 over 0. You cannot write that something is equal to infinity over infinity. You will always lose a point on the AP test, on my test, on any test, if you write that something equals 0 over 0. That does not make sense. So make sure that you check And then you actually have to show each limit individually. I'm going to show you what that means, but you basically need to show that the limit as x approaches c of f of x is 0, and the limit as x approaches c of g of x is 0, which is what allows us to then take the derivatives and apply L'Hopital's rule. If you have to use L'Hopital's rule more than once, you have to show that conditions are met more than once. So really what we're going to do in the rest of these notes is we're going to work through some example problems. You're going to see some cases where you have to do it more than once, some cases where you don't. Anytime you're using L'Hopital's rule, you have to show those limits. You do not have to state, unless a problem specifically asks you to state a theorem by name. On the AP test, you will not be required to state a theorem by name. So you don't have to say by L'Hopital's rule. I'm going to, because I know that that's the one that I'm using on each of these problems. So let's look at some examples. So the limit as x approaches infinity of x over e to the x. So here is how you show the work. Right now in your head, if you use direct substitution, this is going to give you indeterminate form. You do not need to write anything down. You absolutely cannot write this. That is not true. You will lose points for doing that, and that's a silly thing to lose points for. Here's what you're going to do. You're going to say the limit as x approaches infinity of x equals infinity, which is also actually the limit of the denominator, as x approaches infinity of e to the x. Therefore, which I just like to use the little 3 dots for my therefore symbol, although let's make that a little better. Therefore, the limit as x approaches infinity of x over e to the x is equal to the derivative of each of those things. The limit as x approaches infinity, the derivative of x is 1, the derivative of e to the x is e to the x. And I just want you to note this is true by L'Hopital's rule, which I'm just going to abbreviate as LH. That's a pretty common abbreviation. You do not need to state that. I will not take off a point if you do not state that. But if a test says state the theorem that allows you to do this, then you need to make sure you're stating it. If it doesn't ask you to state any theorems, what you have to show is this limit, and then that the original limit is equal to the derivative limit. And this is now equal to 0, right? As the bottom is going to infinity, the top is staying as 1, so that limit is just going to be equal to 0. All right, let's go ahead and look at number 2. Now, we learned another technique for evaluating number 2, but I'm going to go ahead and actually use L'Hopital's rule here as well. So the limit as x approaches 0 of sine of 5x is 0, which is also the limit as x approaches 0 of 2x. Therefore, by L'Hopital's rule, the limit as x approaches 0 of sine of 5x over 2x equals, don't forget your limit. You have to keep writing the limits each time. The limit as x approaches 0, the derivative of sine of 5x is 5 cosine of 5x. The derivative of 2x is just 2. And now if I use direct substitution, cosine of 0 is 1 times 5 over 2 is just going to be 5 over 2. And I went way too far over into this other problem. So why don't you go ahead and pause the video, work through numbers 3 through 6. Remember, you may not have to use L'Hopital's rule on every single problem. Don't forget all of the things that you have learned up until this point. Also make sure that at no point in time are you writing that something equals 0 over 0 or equals infinity over infinity. That is not the case. You must show that the numerator has a limit of 0 or infinity and the denominator does as well. Then you are allowed to use L'Hopital's rule. So go ahead and pause the video. So for number 3, the limit as x approaches 0 from the right of e to the x minus 1 minus x is 0. The limit as x approaches 0 from the right of x is 0. So by L'Hopital's rule, the limit as x approaches 0 from the right of e to the x minus 1 minus x over x is equal to the limit as x approaches 0 from the right of e to the x minus 1 over 1. Which, if I just use direct substitution, now gives me 0, not indeterminate form. So that final answer is going to be 0. Make sure you keep your limits. Make sure you show those conditions at the beginning of the problem. So on number 4, show that the limits both equal 0. So by L'Hopital's rule, the limit as x approaches 0 of e to the x minus 1 minus x over 5x to the third equals the limit as x approaches 0 of e to the x minus 1 over 15x squared. So I just took the derivative. But now I still have indeterminate form if I use direct substitution. You have to state the conditions again. So now I'm going to say the limit as x approaches 0 of e to the x minus 1 equals 0, which is equal to the limit as x approaches 0 of 15x squared. Therefore, by L'Hopital's rule, the limit as x approaches 0 of e to the x minus 1 over 15x squared equals the limit as x approaches 0 of just e to the x over 30x. Now this limit no longer is going to give us indeterminate form, because if I use direct substitution, the numerator is going to be 1, the denominator is going to be 0. That means that this limit does not exist. I can't have 1 over 0. And L'Hopital's rule cannot be applied to do this again. Therefore, this limit just does not exist. Now, when you look at number 5, yes, you could show that the limit of the numerator and the denominator are both infinite, and you could use L'Hopital's rule a couple of times. But don't forget that if you have two polynomials with the same degree, the limit is just the leading coefficients of your highest degree term. So without showing any work at all, you could just say that this is equal to 5/3. You do not need to use L'Hopital's rule, and you could, and it's going to take you a lot more time to do it that way, but you definitely don't need to use L'Hopital's rule. So I would not. I would save myself the time and the energy and not use L'Hopital's rule on that problem. All right, go ahead and pause the video and work on number 6. So on number 6, show that each individual limit is equal to 0. Therefore, by L'Hopital's rule, the limit as x approaches 1 of the original two functions, I do want to see that step. Ooh, except I just messed myself up here. This should have the limit as x approaches 1. I would have just lost a lot of points there. So that original limit equals the limit as x approaches 1 of the derivative, which is going to be natural log of x squared is going to go to 2x times 1 over x squared, over the derivative of the denominator, which is just 2x. So now these 2x's are going to divide out. So this is really equal to the limit as x approaches 1 of 1 over x squared, which is just 1. All right, now we are going to look at some more examples. So number 7, the limit as x approaches infinity of cosine of x over x. The first thing I want you to note is remember to never forget all the things that we have learned before now. L'Hopital's rule does not apply here. The limit as x approaches infinity of the numerator is going back and forth basically between -1 and 1. That's what cosine does. It goes up and down between -1 and +1. So we can't use L'Hopital's rule, but we can use that idea of what's happening with cosine as it approaches infinity. So what did we just say? We just said that as cosine approaches infinity, we're really trapping cosine between -1 and +1. So we can say that -1 is less than or equal to cosine of x is less than or equal to 1. That is always true. Now, if we want to relate this back to what we're actually talking about, we're not talking about just the limit of cosine of x, we're talking about the limit of cosine of x over x. So let's just go ahead and divide all three portions of this inequality by x, which we're allowed to do based on basic algebra properties. And now let's take the limit of all of those things. So the limit as x approaches infinity of -1 over x is less than or equal to the limit as x approaches infinity of cosine of x is less than or equal to the limit as x approaches infinity of 1 over x. So basically what we're doing is we're trapping, oops, I should have an over x here. We're trapping a function that we don't currently know how to take the limit of based on the properties that we know, we're trapping it between two things that we can in fact take the limit of. So let's see what happens when we take the limit of the two outside pieces. Well, the limit as x approaches infinity of negative 1 over x, that's 0, less than or equal to the limit as x approaches infinity of cosine of x over x, which is less than or equal to the limit as x approaches infinity of 1 over x. Well, as x approaches infinity, I'm getting 1 over infinity, which is also 0. So if the limit as x approaches infinity of cosine of x over x is trapped between 0 and 0, that means that that limit in the middle actually must be equal to 0 itself in order to keep this inequality statement true. This is called the squeeze theorem, and we haven't worked in depth with the squeeze theorem, but it's a great strategy to use when you are working with something that you don't know how to find the limit of, but you can trap it between two things that you do know how to find the limit of. So we'll talk about that more later. The other three problems we have here, I think that you can work through. So I'm going to have you go ahead and pause the video, think about all of the different limit strategies that we have learned, and apply them to these remaining three problems that you can see here. Then unpause the video and see how you did. So for number 8, if you use direct substitution, both the limit as x approaches 0 of the numerator and the denominator are equal to 0. You must state that. That means that we can apply L'Hopital's rule and take the derivative of arcsine, which is 1 over the square root of 1 minus x squared, and take the derivative of x, which is 1. And now we can use direct substitution. 1 over the square root of 1 minus 0 is just going to give us 1. For number 9, you can show that the limit of both the numerator and the denominator are going to 0. Therefore, by L'Hopital's rule, that limit is equal to the limit of the derivative. So the derivative of arctan is 1 over 1 plus x squared. I just moved the 5 to the front. The derivative of natural log of x plus 1 is 1 over x plus 1, and then you can use direct substitution. All that fraction stuff is just going to become 1 times the original 5 in front is going to give you that that limit is equal to 5. The first thing you're going to need to do on number 10 is just get one giant fraction. So find a common denominator, multiply x over x minus 2 by x plus 2 over x plus 2 to get one fraction. And since that's basic almost algebra 1 level work, I'm not going to show that step. I'm just going to jump right to that limit. Once I'm here and I have one fraction, I notice that that limit is both the numerator and the denominator are going to 0 when x is equal to 2. So I'm going to show that so that I can use L'Hopital's rule. So showing that each of those separate limits is equal to 0 means by L'Hopital's rule, the limit as x approaches 2 of the original expression is equal to the limit of its derivative as x approaches 2, which then allows us to use direct substitution, which is going to give us negative 6 over 4 or negative 3 over 2 as our final limit. I encourage you to pause the video, look through the table, look through each of these 4 problems here and see how far you can get on your own, and then unpause the video and I'll walk through it with you. All right, number 11. The limit as x approaches negative 3. So first of all, it says giving this table, which gives selected values of a twice differentiable, meaning it is continuous, function, determine each of the following. So if it's continuous, then the limit as x approaches negative 3 of f of x is equal to f of negative 3, since it is continuous. And that limit is 0, or that value of the function is 0. Obviously, if I plug negative 3 into the denominator, I'm also going to get 0. So this is going to be a situation where I'm going to use L'Hopital's rule. So I'm going to say the limit as x approaches negative 3 of f of x equals 0 equals the limit as x approaches negative 3 of x plus 3. Therefore, by L'Hopital's rule, again, you don't have to state by L'Hopital's rule. I am just in the practice of doing it. On the AP test, on one of our tests, unless the question specifically asks you to state the theorem, you do not have to state the theorem. So by that, this limit, the limit as x approaches negative 3 of f of x over x plus 3 equals the limit as x approaches negative 3 of f prime of x over the derivative of x plus 3 is just 1. So this is going to give me f prime of negative 3, which is f prime of negative 3, 9. So make sure you're really clear with your notation. Make sure you don't drop the limit as x approaches portion until you have actually directly substituted into. Number 12, the limit as x approaches negative 3 of f of 2x minus 1 over x squared minus 9. So I can tell immediately the denominator is going to be 0 if I use direct substitution. Let's see what's happening with the numerator. If I plug negative 3 in here, that's going to give me f of negative 7. What is f of negative 7? It's 0. So we are again going to use L'Hopital's rule. So the limit as x approaches negative 3 of the numerator is equal to 0. The limit as x approaches negative 3 of the denominator is 0. Therefore, we can use L'Hopital's rule. So our original limit is going to equal our new limit where we take the derivative. So this is going to be f prime of 2x minus 1. Don't forget that you also need to multiply that numerator by the derivative of the inside, which is going to be 2. All over the derivative of x squared minus 9 is 2x. Now, we should be able to use direct substitution since the denominator is just going to be negative 6. The numerator, f prime of negative 7, f prime of negative 7 is 6. So we're saying 2 times 6. You could leave it just like that. This is pretty easy to divide to just get negative 2. But you remember, you do not have to simplify all the way. All right, looking at 13. Let's look at the numerator first. Well, the denominator, again, is obviously 0 if I use direct substitution. If I use direct substitution on the numerator, I need f of negative 5. F of negative 5, according to this table, is going to be negative 3. And then I need f of negative 3, which is 0. So the numerator and the denominator both have limits that are going to 0. So I'm going to state that those two limits are both equal to 0. Therefore, we're allowed to use L'Hopital's rule to take the derivative. Now remember, you're going to take the derivative of the numerator using the chain rule. So that's going to give you f prime of f of x times f prime of x. And then the derivative of the denominator is just going to be 3. And then if I use direct substitution, I'm going to get f prime of f of negative 5 times f prime of negative 5 all over 3, which is going to give me 9 times negative 1 all divided by 3, which is going to be negative 3. Number 14, the denominator, that limit is obviously going to be 0. Let's check what's going on with the numerator. F of negative 7 is 0. F of negative 7 is 0. F prime of negative 7 is 6. So either way, the numerator is still going to multiply to be 0. So we are going to start by showing that both of those limits are 0, so we can use L'Hopital's rule. So therefore, that limit is going to equal the limit as x approaches negative 7. The denominator is just going to be 1. The numerator is going to be the product rule, which I did not save myself enough room for. So it's going to be f prime of x times f prime of x, so f prime of x squared plus f of x times f double prime of x. So let me rewrite that so you can actually read it. All right, I still struggle to fit that in there, but let's go ahead and directly substitute now. Since the denominator is going to be 1, we don't have to worry about having any issues with our limit. We can use direct substitution. So f prime of negative 7, f prime of negative 7 is 6. So this is going to be 6 squared plus f of negative 7 is 0, so I don't even care what f double prime of negative 7 is, because that is still going to be multiplied by 0. So we're going to end up with 36 as our answer to this limit. Okay, here we are with our last two problems. We are going to use this graph to find each of these following limits and use the given information in the problem. So why don't you go ahead, pause the video, see how you do on your own without me helping you, and then unpause the video and see how you did. 15, the limit as x approaches 4 of g of x, which is clearly continuous at negative 4 based on the graph. That limit is going to be 0 based on the graph. The denominator, if I plug in 4, that's also going to be 0. So I'm going to start by showing that both of those limits are equal to 0. Therefore, we can use L'Hopital's rule. So conditions are stated by L'Hopital's rule. That original limit is going to be the same as the limit as x approaches 4 of g prime of x over the derivative of the denominator is just going to be 2x minus 2. Now, just glancing at the denominator, if I use direct substitution now, I'm going to get a value, and that value is going to be negative 6. Let's see what happens in the numerator. G prime of 4 is asking me what is the slope at 4, and looking at that slope right here, that slope looks like it's negative 1, down 1, right 1. So negative 1, oops, this is positive 6 in the denominator. Negative 1/6 is going to be that value. And last but not least, number 16, the limit as x approaches 1 of x g of x. So let's see what g of 1 is. G of 1 is 0. So that is going to be 0. Obviously, if I plug 1 into the denominator, that's also going to be 0. So the limit as x approaches 1 of x g of x equals 0, which equals the limit as x approaches 1 of x minus 1. Therefore, by L'Hopital's rule, this limit, the limit as x approaches 1 of x g of x over x minus 1 equals that derivative, the limit as x approaches 1. The denominator is just going to become 1. We're going to use the product rule on the numerator. So the derivative of x is 1. That's going to give us g of x plus x times g prime of x. And now we're going to use direct substitution. So g of 1, we already said, is 0, plus 1 times the derivative at 1, or the slope of the line at 1, and that slope looks an awful lot like 1/2. So times 1/2, which is going to give me that this overall limit is 1/2. So a couple reminders, make sure you always state the conditions. Each separate limit is equal to 0. That is why you are allowed to use L'Hopital's rule. Make sure you always state that the original limit is equal to the derivative limit. Don't drop your limits anywhere along those lines. And then also don't forget that you cannot at any point in time say that something is equal to 0 over 0 or equal to infinity over infinity. That will make you lose lots of points that I do not want you to lose on both my tests and the AP test. So never say that something is equal to 0 over 0 or that something is equal to infinity over infinity. It doesn't make mathematical sense to say that. Make sure that you're always showing those conditions, showing the limits, and really being accurate. But also, and I know you're tired of me saying this, don't forget all of the other tools for limits that we have learned up until this point. We just added a tool. We added a new limit tool in, but that doesn't mean everything that we have learned before this point no longer applies. So we've added a tool. Make sure you have your tool belt full when you are working on problems involving limits. Looking forward to supporting you with this in class. Thanks for listening.